Hey everyone, in today's video we're going to start lesson number 6 for abstract algebra, which is going to be about quotient groups and normal subgroups. So this is probably one of the most important things you'll learn in abstract algebra, at least the idea of what a quotient group is. So I really recommend that you take your time with this lesson or with other lessons where you're learning quotient groups because they're confusing. So I'm going to try to introduce them in an intuitive way. And you're just going to need to practice with them to get a good grasp of how they work. You're going to need to struggle with the definitions and with the examples. Okay. So the idea behind quotient groups is we're going to use our equivalence relations we defined last time. So the idea is, can you take a group and find another group by using an equivalence relation? And so you want to find new groups. Using an equivalence relation. This is kind of a natural idea in math, to take something you do know, a group, and try to find new things that may have even more interesting properties. So the way we're going to do that is through this definition. Okay. The set, usually called G mod an equivalence relation, squiggle, is the set denoted G, this kind of slash squiggle, which means G mod the squiggle. You might kind of interpret this as division, which is not a bad way of thinking about this, because it's kind of like taking a group and finding something smaller. Equals is just going to be the set of all the equivalence classes. So all the equivalence classes of elements of G for all G and G. Okay, so to understand this, let's just do a quick example. So let's let G be the integers, of course under addition, where G is equivalent to H if and only if G is congruent to H mod 3. Okay. So we learned from last time that the equivalence classes of 0, 1, and 2 partition the entire integers. So we get that G mod our equivalence relation is just the set of the equivalence class 0, the equivalence class 1, the equivalence class 2. Okay, perfect. So it's just kind of like, whereas when we were talking about how the equivalence classes partition the integers, that was when we were taking the union of them, because each equivalence class is actually a set themselves. The set of all elements equivalent to this element. But this is the set of those equivalence classes. It's not the union of them. It's just a set that's collecting them up. So that's a slight difference between those ideas, but it does mean something. So you should really think of G mod, the equivalence relation, to be this set of equivalence classes. Just like combining all of them. And I think the best way to understand how these work is something called the quotient map. So the map, we're going to use the pi as as our function from G to G mod our equivalence relation, where, and it should be kind of natural how this map should work, it sends a group element G to, of course, its equivalence class in the set of equivalence classes. Hopefully that's pretty natural. Is called, or at least I'm calling it, the quotient map. Quotient map of our group and our equivalence relation. Okay. So in this case, I mean, it's pretty simple, you know. It's just like pi of an integer is just going to go to that equivalence class of that integer. So like for as in our example above, pi of 4 is going to be equal to the equivalence class associated with 4, which is the same as the equivalence class associated with 1. Okay. So let's note some things about this function. First, we note that pi is surjective. This is clear from the definition because, I mean, if G mod the equivalence relation is the set of all equivalence classes, and pi just sends elements to their equivalence classes, it's got to be surjective. And this means we can basically fully understand all the elements on our G mod equivalence relation just by how pi works. And we also get this property that pi of G equals pi of H if and only if G is equivalent to H. Now, of course, like, you might want to hope that you could create pi to be injective in some way because we love bijective functions, but there's really no way, because if your equivalence class or equivalence relation is meaningful in any way, you're going to have elements that are not equal to each other in the group but are equivalent to each other, which will then not satisfy injectivity. Okay. So hopefully then you should say, well, shouldn't we apply this equivalence relation or this idea of a quotienting out by equivalence relation to the stuff we talked about last time with the subgroup acting on its group? So let's apply to when H is a subgroup of G and H acts on G. Okay. And we're going to define the set as, it's going to be called G mod H. So instead of modding by the equivalence relation, we're just going to call it G mod H. The set G mod H, or denoted G slash H, is G slash H equals the set of equivalence classes, and in our case, when H acts as a subgroup on G, this is just the set of right cosets for all G and G. Now, I should note that G mod H is actually isomorphic, or I should say bijective, has a bijection, to the set of left cosets. And so this is all those sets GH instead of HG. And it happens to be that the left cosets is a more standard notation for G mod H. And since that's probably what's going to show up in the class you're taking and maybe further exploration with the field of abstract algebra, I'm going to introduce it that way. So we're instead going to be thinking of G mod H as the set of left cosets. Now I wrote it as such because it's consistent with how I've introduced the subject so far, but from now on we're going to use the idea of left cosets. So we're going to think of G mod H as GH for all G and G. These are slightly different sets, but it should be noted that there's a bijection between them, and we'll see actually when G mod H is a group, they actually end up being the exact same. So there's really nothing to worry about. Okay. So 2 things to note. First is that the size of this set is just the size of this set is just the index of h and g, but we proved last time by Lagrange's theorem that this is just the order of g divided by the order of h. Okay, so that's good. We instantly know the size of g mod h. That's somewhat helpful. And we also note that we can apply our quotient map to this. So pi now goes from g to g mod h, where we get pi of g equals gh, so the left coset associated with g. That's because this is the equivalent class and the equivalence relation. We also get that pi of g equals pi of g prime, where these are just two different group elements. If and only if, well, I need g to be in the left coset of g prime, but this is just equivalent to g equals g prime times h for some h in h. Okay, so this is basically all the information you need to know. Pi of g just sends elements to this, and they're equivalent in this way. So you can say pi of g equals pi of g prime if and only if there exists h and h, so that g equals g prime times h. So you know how to describe elements in the quotient group, or I should say the quotient set, and also how to know if they're equal or not. Okay. So a natural question should arise. Natural question. It's good to get practice thinking of these things because a lot of math is just formulated as these natural questions. You start with something called a group and you come up with these axioms and you're exploring ideas like g mod h. And so a natural question is, when is g mod h a group? Okay, let's explore that. To be a group, you not only need a set, but you also need a multiplication law. So let's try to define that. Idea, we can define the multiplication pretty naturally. So define multiplication on g mod h by pi of g1 times pi of g2. Remember that these are elements in g mod h. So multiplying them together should equal pi of g1 times g2. And of course, this multiplication is in the group G, whereas this multiplication is in g mod h. So the reason why we might want to define this way is we'll see if it ends up being a group, we then have pi as a homomorphism, which is just a very helpful fact to have. So you can also think of this as saying, if you like to think of it in terms of cosets, g1h, the coset g1h, times the coset g2h equals the coset g1 g2h, which should be pretty natural. Okay. So let's see if this has the regular things we would want a group to have. That mean associativity and identity and inverses. Let's do associativity first. Okay, well, we see that pi of g1 times pi of g2 all times pi of g3, well, this equals pi of g1 g2 times pi of g3 equals pi of g1 g2 g3. Then if I put the parentheses on the other way, I get that pi of g1 times parentheses pi of g2 times pi of g3. I know, a lot of pi's. This equals pi of g1 times pi of g2 times g3, once again equaling pi of g1, g2, g3. If you really wanted to be strict, this equal sign and this equal sign here really comes down to the fact that the group itself is associative. G is associative, which makes G mod H under this multiplication law also associative, because this is equal to that, because they're all equal to pi of G1, G2, G3. Okay. Now let's see if it has an identity. I think it's good practice if you try to guess what the identity should be. And if you have a guess, let's see if you're correct. Let's let pi of 1 in G mod H be the identity. Let's see if it works. Well, we get pi of 1 times pi of G equals pi of 1 times G, which is pi of G. Works the other way around. Pi of G times pi of 1. Perfect. And if you're thinking about this in terms of cosets, that just means H, the actual set H, is the identity in G mod H. Hopefully that should be pretty natural. If we're thinking about equivalence classes, the thing we're modding out by makes sense for that to be the identity. Okay, inverses. This one's also pretty easy. We see that for all G and G, pi of G times pi of G inverse equals pi of 1, which is the identity. Okay, so we get inverses as well. Perfect. So now you might be saying, oh my gosh, we've fully defined a group. This is amazing. G mod H is always a group. But I've kind of led you astray. There's one problem, which is our multiplication even well defined? What do I mean by that? Okay, well, consider this. Okay, let's say I had pi of G1 times pi of G2 equals pi of G1, G2. But then I also had some elements, pi of G1 prime, which is equivalent to G1. So I'm saying let's choose some G1 prime such that they're in the same left coset, and some G2 prime such that they're in the same left coset. And now I'm multiplying these guys together, which equals pi of G1 prime, G2 prime. And my question is, what goes here? Are these equivalent? Are they equal to each other? Because for our multiplication to be well defined, they have to be. But if they're not, then we have a serious problem. So we need to check that. The reason why this is a concern is because, well, you could easily have two elements which create the same left coset. It happens all the time. So the question is, how do you choose one, right? I just chose G1, but I could have chosen this G1 prime. It gives me the same thing. And if I get different things when I multiply, that's a problem. So I need to make sure I get the same thing every time. So, okay, let's see. What do we know? Well, we know that G1 prime equals G1 times H1 for some H1. And of course, G2 prime equals G2 times H2 for some H2. This is just, by our definition, if they're in the same left coset, this is just has to be true. Okay. So we want to show, or we want to ask at least, WTS means want to show, when pi of G1 prime times pi of G2 prime equals pi of G1, G2. Okay, well, I get pi of G1 prime, G2 prime equals pi of g1 h1 times g2 h2. And I'm going to simplify this a little bit. If you're multiplying on the right by some element in h, well, this just has to be equal to pi of g1 h1 g2. Because, of course, multiplying by the right by an element in h doesn't change your left coset, right? I mean, like, the left coset of gh, h, is the same as gh. Just because h is already in h. Like, it doesn't change anything. Of course, you can prove this rigorously using the definition up here. It's very easy. Now we want to show when is pi of g1 h1 g2 equal to pi of g1 g2. This is an interesting question because now the h is no longer on the right. It's dead center. So it might be weird what happens. I'm not sure. Let's figure it out. Well, I do know, but we're going to figure it out. So this happens when there exists an h in h such that g1 h1 g2 equals g1 g2 times h. Okay, I can multiply by g1 inverse on the left. This implies that I get h1 g2 equals g2h. And this finally implies that I can rewrite this as h1 equals g2 times h times g2 inverse. Okay. Now, you might recognize there's a reason why I chose to write this expression this way. And you might recognize I introduced in a much earlier lesson the idea of the conjugate, which is taking an element and multiplying by g and g inverse on the left and right respectively. We see that come up again here. And this is actually not always true. You don't get this to always be the case for some subgroup H, where taking any random element g, multiplying by on the left and g inverse on the right, you get another element in H. Because this is not trivial, we come up with a whole new definition for it. So to rewrite this, we require that for all h in h and g in g, g times h times g inverse is in h. If this is the case, then our multiplication is well defined. If it's not the case, then it's not well defined. So, because of that, let's try to then come up with this definition for subgroups that satisfy this property, and then we can apply that. Okay, definition. A subgroup H is normal, so it gets this new symbol, normal in G, is normal if GH, G inverse is in H for all G and G and H and H. Okay. This is also sometimes written as GH, G inverse is in H. Because it's kind of the same way if you're checking all H and H, you can replace that little h with a big H. Okay. And of course our corollary from this definition is that G mod H is a group if and only if H is normal in G. I love writing this symbol, it's so much fun. Okay, let's do some examples to understand this definition. Okay. So the subgroups G and just the identity are automatically normal in every group G. This is just because, well, let's do it by the definition. For just the group G, GH, G inverse has to be in G. I mean, that's just, multiplication is closed. It has to still be in the group. So this is, of course, in G. So we get that G is normal in G. And then for the identity, g times 1 times g inverse just equals g times g inverse equals 1. So that's also normal. So you get g and 1 are normal in G. So then the question is, what is their quotient group? Well, G mod G is going to be equal to 1. And G mod 1 is going to be equal to G. You can verify these for yourself. I think the easiest way to do it is actually just look at what the size of these quotient groups should be. Okay, another example. If G is abelian, then all subgroups are normal. Are normal. Okay, let's figure out why are normal. So let H be a subgroup of G. We get that for all G and G, H and H, GH, G inverse, well, since G is abelian, I can commute elements. So I can swap around G inverse and H to write G, G inverse H, but G inverse is just 1, which is H, which is, of course, in H by definition. Thus, H is actually normal in G. So that's just, a quick fact. If you know your group is abelian, you don't have to worry about proving that a subgroup is normal. You know that it's always normal. Okay. So let's let G be our integers again. And let's let our subgroup H be 5Z, which is going to be equal to the set. It's going to look like this. -10, -5, 0, 5, 10, so on and so forth. So it's all like multiples of 5. Then you can verify that G mod, our subgroup H, is going to be equal to pi of 0, pi of 1, pi of 2, pi of 3, pi of 4, and then, yeah, that's it, pi of 4. Okay. This is the exact same idea as before when we were doing the integers and the equivalence relation was taking things mod 3. And this is like taking things mod 5. Our equivalence classes are 0 through 4. So these are all things that are multiples of 5, 1 away from a multiple of 5, 2 away, 3 away, 4 away. So, since G is abelian, we get that G mod H is a group. Since, of course, H is normal, since every group, a subgroup is normal when G is abelian. And we also get that since the order of our set is the amount of equivalence relations, I mean, we wrote them out here, so it's 5, then our group must be cyclic. We proved last time that all groups of prime order are cyclic. So G mod H is cyclic. In fact, if you're curious where the notation Z mod 5 comes from, it's really the same as writing Z mod 5Z. In fact, a lot of the times people will write this instead of Z mod 5. I kind of think that Z mod 5 is more compact, but this is more relevant because it's derived from this idea, taking the integers and modding out by 5Z, this subgroup 5Z. Okay. One more example. So we're going to basically define a new kind of group, subgroup in groups. So let Z of G denote the center of G, where Z of G equals all those elements, let's call them H and G, such that GH equals HG for all G and G. So you can basically think of it as all those elements which commute with every element, where if you put it, you can switch things together. Okay. Then Z of G is a normal subgroup of G. This is pretty clear because we get G inverse equals G times G inverse times H, because you can switch anything around, which of course is H in Z of G. Okay. So the condition that a subgroup is normal is not an easy one. It's not easy to satisfy at all. Because of this, we're going to try to define some things and characterize normalization. So hopefully you have an easier time of deciding whether something is normal. Definition. The normalizer of H and G is the subgroup which is called n sub G of H, which equals those G and G such that GHG inverse is in G, or sorry, is in H. So basically you can think of this as like all those elements in G where the normal condition is satisfied. And so of course, you know, what this implies is that if NG of H, their normalizer, is the entire group, then H is normal. So this should lead us to coming up with a theorem of different ways to characterize normalization. So the theorem says the following are equivalent. That's what this stands for. TFAE, the following are equivalent. First one. H is normal in G is equivalent to NG of H equals G is also equivalent to GH equals HG for all G and G. This is where I mentioned before, the left and right cosets are the same, which means if you wanted to define the quotient group as all those left cosets, or if you want to define it as all those right cosets, if it's a group, it really doesn't matter. And 4, which is GH, G inverse equals H for all G and G. And honestly, these should be pretty clear for you. So the proof is going to be left as an exercise. Hopefully they should be pretty straightforward to prove. Okay. And before we end this lesson, just a quick note, and before I get to the exercises, is that we get if H is normal in G, then the map pi from G to G mod H is a surjective homomorphism. And of course, the proof is pretty straightforward. I mean, we just know that pi of G1 times pi of G2 equals pi of G1, G2 by our definition. That's what we wanted. We wanted to define multiplication in a way such that we get this homomorphism naturally arising. And this is really helpful. So now if you want to describe G mod H, well, you have a homomorphism. You have some way to describe G mod H just from the group elements. I mean, that's basically the best you can do, which is why we usually use pi to describe the cosets instead of just thinking of them as cosets. Okay. And I'm going to leave you with some exercises to give you more practice with quotient groups. Okay. First one. So let's let G be cyclic. And I want you to prove that for all subgroups H and G, that G mod H is also cyclic. Cyclic. And a part of this proof is proving that, of course, H is normal in G to even know that G mod H is a group. So that's something you also have to do, which is that all subgroups of a cyclic group are normal. And then you have to prove that they're also cyclic. Okay. 2. Let H be a subgroup in G with the index of H being equal to 2. And then I want you to prove that H is actually normal in G. Okay? This one is slightly challenging, so just for a hint, you should try to compare the left and right cosets. And then finally, find all normal subgroups of D4. So this is, symmetries of a square. And try to find their associated quotient groups. Okay. Thanks for watching.